Thank you all for like coming today. You know, like since today's well-being day, and then most of y'all will have like to take the trouble to specifically come all the way here just for today's session. So today, what I'll be talking about is really about the motions of planets in the sky. And to clarify, this is actually part one of a two-part talk. Why is it a two-part talk? Well, there's just too much things to be crammed inside one talk, unless you all want to be here for like 2+ hours, right? Just listening to me to like ramble on and on and on about things, right? But then what this talk will be is really more focused on like, it require you to like engage a bit more with the content on the slides, basically. So a lot of the explanations will rely on some bit of geometrical intuition, like spatial arguments. And then I'll be having quite a bit of like diagrams here and there, right? So at any point, if you want to have like some more time to maybe parse the diagrams and like look at things or anything you want to clarify, feel free to stop me. Don't make it just like a purely one-way thing, and then at the end of it, it's like you all are just lost everything, right? So, okay. So why do we even bother talking about planets at this stage, right? Because we all know that like we have Newton's laws of gravity. They more or less accurately describe the motions of our planets, and like it's a solved problem since like the 1700s, you know, right? But well, it's true that since the Copernican revolution and like the advent of Newtonian physics, that we can like just throw equations to supercomputers to predict everything for us. Well, the picture of like the solar system that we have doesn't necessarily correspond to what we actually see when we go out, you know, and just check the motions of the planets, right? So in fact, like despite being a so-called like discredited theory for like many hundred years, geocentrism does one thing right, which is that it describes what we actually see out there in the world from like the perspective of an earthbound viewer, right? And even though most of the features of the theory that we see are artifacts of like perspective effects, right? But perspective effects themselves are still, I think, like quite interesting to talk about and quite interesting to understand. And it is that barrier that we need to overcome to like finally draw the link between like our nice heliocentric model of the solar system to what we actually see out there in the sky, right? So just to give like maybe a bit of motivation to what I mean by how planets look from a geocentric orbit, you can just take a look at this like short animation. Okay, just skip over. Yeah, you can just take a look at this short animation. Right, so what this diagram is, right, is that you have the Earth right at the center as a fixed point. The edges over here, they are basically fixed to the stars, right? So every time this part of the orbit, we have the Earth and the line of sight right here. It's pointing at a particular fixed direction in the stars, right? So that means that if you plot the path of the sun on this diagram, it follows this blue circle right here. And then it basically goes once around the Earth, like once per year. So this is how you can understand the diagram. The black line over here is the trajectory of Mercury. The blue one is the trajectory of Venus, while the red one is the trajectory of Mars, right? So as you can see, the radial distance from each point on the path corresponds to the distance between the Earth and the planet, right? And you can see that this distance is constantly changing and changing as like both the planet and Earth revolve around the sun, creating like this kind of like complicated patterns, right? So just an overview of like where am I going with all of this, right? So I'll be covering like mainly from the perspective of like reference frames, right? So we start off with what we know in the heliocentric frame. We move to some concepts about like how we look at the sky from the Earth's perspective, and we sort of combine the two in a special frame of reference that we call the Sun-Earth frame, right? So what do we know about the solar system? These are very familiar ideas for most of us, right? So there are 8 planets of the solar system, used to be 9. Pluto got downgraded in 2006. We have 4 inner planets and 4 outer planets, but the classification that we're interested is the division between inferior and superior planets, right? So the 2 inferior planets are Mercury and Venus, and they are inside the orbit of like Earth's orbit around the sun. While everything else, Mars, Jupiter, Saturn, Uranus, Neptune, they're all called superior planets, right? So in heliocentrism, it's also an approximation, right? Because really, what the heliocentric frame does is that it takes the sun and the distant stars as fixed reference points to like describe the motion of the planets, right? So because in order to describe a reference frame, you need like your origin point and you need to fix the directions, right? So you just take the distant stars as the thing that's like fixing the directions. So this is only an approximation because as we know, the sun and all the stars, they're all orbiting around the Milky Way. But this is also like happening at such a slow rate that we might as well take like the distant stars and like the sun as fixed points for us to describe the motions of the planets, right? So one convenient way to understand the orbit of planets around the sun is to use what? The physicist's favorite tool, right? The right-hand rule. So if you look down at the north, at the plane of the solar system, and you take out your right hand, you curl it around and let your thumb face north, the orbits of the planets will follow the direction which your fingers curl, right? So quite nicely, this also is the same as like our angular momentum vector for the solar system, but it doesn't really matter for us. But this right-hand rule is a convenient way for us to like remember which direction do the planets orbit, right? So yeah, this will be quite helpful later on. So the second point that is important for us to know about are Kepler's laws as usual, right? We have Kepler's first laws, second laws, and third laws, right? So really, the only important law that I really want to discuss today is Kepler's third law, which tells us that the square of the orbital period is proportional to the cube of the semi-major axis. But even though you don't even need to like understand this, just in general, you just know that if a planet is further away from the sun, then it moves slower. And why do I say the first and second laws are not relevant in this case? Well, of course, there's a lot of like models of the solar system you can build, all the way from simple like concentric models to like ellipses in a single plane, which is what like physics students have to deal with when we do homework, right? But then when you design rockets and spacecraft, you need to deal with elliptical orbits that are oriented in 3D space, because like not all the planets are lying on the same plane, and you ended up having with like to use 6 numbers to describe each like orbit of a planet, right, which is a pain. And you go one step further, you can talk about like perturbative effects, which is well beyond the scope of this talk. But because all we are doing is just to restrict ourselves to concentric circular orbits, right? So that tells us directly that the period of a planet's orbital or orbit around the sun is proportional to its like orbital radius by this relation. So all the equations aside, what's more helpful is to just have a view of like the concrete numbers, right? So this is a table of the distance of each planet's distance away from the sun as well as its orbital period. And the immediate thing that you should notice is that for the inner planets, their distance from the sun is very, very tightly packed together as compared to all the outer planets, right, which are like more spread out. So in this graph, you can see that Mars, Venus, Mercury, and Earth, they're all like in this really tiny, tiny circle here, while the orbits of Uranus, Neptune, Saturn, and like Jupiter, they're all like spread out quite significantly, right? And then what the effect of this that there's this huge cliff in the middle, you know. So the orbit of Mars is on the order of like 1.88 years, while Jupiter takes a massively long 12 years to orbit the sun. So what's the point of going all through this? So you want to be able to put all of this together into sort of a coherent picture, right? So let's say you want to figure out the motion of the planets. You can do it yourself, right? So you just draw the sun in the center, draw the orbit of the Earth, draw the orbit of the outer planets. Then what you need to remember is the direction of the orbits, right? You just imagine you're looking down at north. Then you just take your fingers, you curl them around. That tells you that the planets are orbiting counterclockwise around the sun, at least when you look at the north, right? And you know that because when a planet is closer to the sun, it orbits faster, then that tells you that at each time interval, the blue planet might travel this much, but your red planet can only travel that much. And based on a diagram like this, you can start asking yourself questions like, where in the sky do the red and blue planets appear relative to each other, right, at every single time interval? So let's say that you're at the first time interval, the red planet is in this direction. The second time interval is at this direction. The third time interval is at this direction, and so on, right? So you can sort of like create like small pictures for yourself like this. But then I'll obviously be going through all of this like from a more guided, approach, with a more guided approach, right? So the next thing we need to know when it comes to understanding the orbits of planets is to understand how, in general, the sky moves, like from a perspective of someone on Earth. So that's where the geocentric frame really like comes in helpful, right? So when we use a geocentric frame, because we take the stars as a fixed reference point, we sort of imagine them as being part of this huge imaginary circle that is like a fixed firmament of stars with the observer at the center. And because the stars are so far away, we basically neglect any kind of parallax effects when the Earth like orbits around the sun. Because in reality, when the Earth orbits around the sun, your distant stars will wobble very, very slightly because of the parallax effect. But this motion is so small that you can basically just treat the stars as fixed points, right? And apparent motion aside, the stars do move by themselves, but because they are so far away, their motion is basically also imperceptible to us. So the celestial sphere has one single axis of rotation, which, come in. Huh? Okay, the celestial sphere has like a single axis of rotation that is aligned from south to north, right? So this is the same axis as the Earth rotates around like each day, right? So for example, we have like the celestial poles and celestial equators on the sphere, on this celestial sphere, right? So the celestial equator passes right above where the equator on Earth directly is. So you can think of like the celestial sphere as something that's the surface of the Earth that's blown up all the way to the sky, right? So our North Pole is directly pointing towards where the North Celestial Pole is. And this celestial sphere, it rotates 360 degrees over a period of 23 hours, 56 minutes, and 4 seconds. And if you notice, this is not 24 hours. So the reason for this is that this is really how fast the Earth takes to orbit on its own axis, like objectively out there in space. Meaning this is like with respect to the stars, right? But because the Earth is also moving around the sun at the same time, there is this extra like 4 minutes that's not being like, that there's also like not being counted in this number. So as the Earth moves around the sun, the Earth has to like rotate a bit extra in order to compensate for the distance that it moves around the sun. So this is why there's this difference. So with the celestial sphere, the stars seem to rise in the east and set in the west, at least from the perspective of an observer on Earth. But we know that from a heliocentric frame, the Earth actually rotates according to the right-hand rule, right? So you can imagine that, like putting up your thumb along that, like pointing towards north, then you know that the Earth is supposed to be rotating in this direction. But then if you look from the perspective of someone on Earth, the whole sky seems to rotate in the opposite direction, which is from west to east. So in a short amount of time, we can sort of regard the motion of the sun and planets as being sort of fixed on this like celestial sphere, right? Because over the course of a single day or a few days or week, the sun and the planets, they don't really move that much. So we can just treat them as being like fixed points on the celestial sphere, right? But obviously, like when we talk about the motion of planets, I'm talking about on the time scales of like, let's say, several weeks to months over like years, right? So this is a totally different time scale from like the motion of the Earth on its own axis over a single day. So that means that we need to separate these two kinds of motion, which contribute to how the planets move in the sky, right? So on a daily basis, you see the planets rise from the east and set in the west. That's the daily rotation. But when we talk about planetary motion, what we are talking about is how the planet moves with respect to the background stars. So just to give an intuition for like how this looks like, this is basically a time lapse of the sky over like the course of a single day, right? So you can see that even though the planets do move quite a bit within the single year, over a single night, you can just treat them as basically being fixed points on the celestial sphere. And that means that you'll carve out a single path along with the rotation of the sky. So one useful, okay, even though I said that we are going to be neglecting the rotation of the Earth itself, it is still helpful for us to determine like the cardinal directions. Exactly because like our north, south, east, and west are all like defined by the rotation of the Earth, right? So how does this work? Okay, imagine your observer standing on this side of the Earth, right? So when you face this way and you rotate this way, you can see the stars on this side rising up, right? And as you know, everything rises in the east and sets in the west. So this tells you that this direction is east for you and this direction is west for you. But the confusing thing is that once the Earth rotates to the other side, this is your east and this is your west, right? Right, so east and west, as you must realize, they are not really fixed directions in space, you know. It really refers to the direction of rotation, right? So that means that a counterclockwise rotation means a rotation going from west towards east, you know, and from here, same thing, west towards east, right? So this is convenient for us because this also allows us to sort of define time in terms of like spatial directions, right? So let's say you have the sun right here. You know that when you're on this side of the Earth and the sun is right above you, you know that it is 12 noon, it's 12 p.m., right? But you know that at this point, because the Earth is rotating counterclockwise in this direction, that means that if you look towards this side, towards the sun, your line of sight just starts moving in this direction. And you know that the sun is sort of like setting below the horizon. And you know that this is the exact point where sunset happens. So when you look up at the sky at this part, this is where the sky, this is basically where the part of the sky that is right above you at 6 p.m. during the evening. And if you just go all the way here, this is when you're opposite the sun, the sky right above you is like this part of the sky opposite the sun is the part of the sky that is like right above you at 12 a.m. Right? So same thing, when you go all the way to this part, then you can sort of see the sun rising in the horizon, right? So you know you're facing east over here, and the part of the sky right up here corresponds to like the 6 a.m. part of the sky. So I don't know if it's like too confusing for any of you, but there's basically a very, very natural one-to-one like relation between the directions in the sky and also like the time that you're at on Earth, right? Because like precisely because our time is like determined by the angle of the sun toward as compared to the observer on Earth, right? So if you imagine as the Earth orbits around the sun, it's gonna move in this direction, right? Wait, can I see my notes? Right. So let's say like this part of the sky is the sky that you see at 6 a.m., which is the winter sky. Then the opposite at 6 p.m., the part of the sky that you're looking at is sort of like the summer region, right? Because they are opposing parts of the sky. That means that further on in the Earth's orbit, let's say it moves like a quarter of an orbit around, then the part of the sky you're facing is the winter sky at 12 a.m., while your sun is all the way in Scorpius in the summer region, right? So that is from the sun's perspective. You have the Earth moving over here. But at the same time, you also can think of this as the sun moving from the bottom all the way up here towards like the 12 p.m. area, right? So this gives you like a natural way to sort of like switch between sort of like geocentric perspective of looking things towards like a more like heliocentric one, or vice versa, right? So so this is exactly what the concept of an ecliptic plane is, right? So like over the course of a year, the sun traces a path around the Earth, like in the sky, right? And then this is exactly the same thing as the plane of Earth's orbit around the sun. It's just like a matter of like switching the direction they're looking at. And one thing to note that this plane is inclined at 23.5 degrees relative to the celestial equator. And this is precisely because Earth's axis is tilted in the heliocentric frame at 23.5 degrees from its orbit around the sun. So this animation just sort of like gives you a good idea of like how this path is being traced out, like with respect to the background stars, right? So one thing I want to highlight is that when you're looking down at the north, the Earth rotates counterclockwise around the sun, but at the same time, if you switch to a geocentric frame, the sun also moves in a counterclockwise direction around the Earth. So when you start switching like your reference frames, the direction doesn't change in this case, right? So the Earth orbits counterclockwise around the sun. If you switch around, the sun also orbits counterclockwise around the Earth. So the ecliptic plane is also the approximate plane of the solar system, right? Because as you can see over here, all this is the ecliptic, and the orbits of the planets are just very, very slightly offset from the ecliptic plane, right? And if you notice, the planes of all the other planets seem to be like tilting more towards this side versus the other side. This is just an artifact of like Earth's own orbit, right? Because compared to the other planets, Earth's orbit is more tilted towards this side. So if you look at the ecliptic, which is basically you're using the Earth and the sun as the reference points, right? That means that all the other planets' orbit is sort of like look tilted towards this side. So yeah, you don't have to worry about that too much. But for our purpose, we can sort of assume that all the planets are really orbiting on a single line in the ecliptic plane. So we have this photo, then you can see the whole line of planets right here, right? Then that tells us directly that this must be where the ecliptic is crossing. So I have 3 questions. What is the direction that the planets are orbiting? Second, what time is the photo taken? And third, what do you think the moon phase is currently? Can anyone try to answer? First clue is that you can see that this part of the sky is the eastern sky, right? So that means you can start applying a right-hand rule to sort of tell where the direction that the planets are orbiting. Anyone? Is it orbiting this side, downwards, or like upwards? Anyone? Yeah.
I mean, planets are moving in this direction because I think photo might have taken around 6 a.m. because you can see Mercury is a rising star on the east.
Yes, it's true. It's the morning, right? Because you're looking at east and you can sort of see Mercury and Venus right here. So because Mercury and Venus are always near the sun, that tells you that the sun is like right here near the eastern horizon. That means that it's near morning. So yes, that's correct. That's the second question answered. Anyone can tell us? Ah, you're saying this side, is it? Well, I mean, what is true that the sun rises this side, then over time the planets will rise this side. But what I mean is that what is the direction the planets are orbiting within around the sun? Yeah, this is what I sort of touch on about the difference between daily rotation and the orbit of the planet itself around the sun, right? So due to Earth's daily rotation, you have the planet sort of like rising up like in a single day. But over the course of multiple days, this is not what you see, right? So that's what we are talking about. Okay, in the interest of time, so applying the right-hand rule, east is this side, then you know north is somewhere there. So that means you just apply your like right-hand rule this side, and that means that the orbit of the planets are curving towards this side. So your planets are really like moving in this direction. Wait, no. Where's north? Where's north? North, south. East is there, or east is west. Yeah, no. North is there. North is there. So that means that the planets are like moving down this side, right? When you use a right-hand rule, right? Sorry, I got confused there. But actually a good way to sort of like remember, if you don't really like this kind of like geometric visualization, is just to remember that planets move from west to east, at least like when we are looking at them from Earth, right? So the last thing is that, the moon is a crescent moon, right? And because the moon is moving towards the sun in this direction, that means that its face is starting to get like get like narrower and narrower. That means that it's a waning crescent. So over the course of the day, we know that all the planets, like we also move because of the Earth's daily rotation, right? And so this traces out sort of a latitude circle in the sky, right? Because we are sort of like assuming that within the time span of a single day, you can sort of like treat the planets as sort of like fixed point, right? So it just like traces out this circle, which is exactly parallel to where the Earth's equator is moving, right? So if your planet is here, it's fixed, it just goes around here. If your planet is here, it's fixed, it also just goes around here. This is the same thing that happens from the sun, and this is exactly the reason why we have seasons, and this is why at northern latitudes, the sun takes a longer, like the days are longer and like the nights are shorter. Well, obviously on equator, that's not what we see, right? On equator, the planets and the sun, yeah, they mostly like rotate around the sky in this direction, directly from east, and they set in the west, like just crossing overhead. So this is like the perspective from Singapore. Well, we all know that at northern latitudes, right, we have the sun moving along this path during summer, which causes the days to become longer. And during winter, the sun will be at a lower latitude, and then it sort of like moves in this path, and this path is sort of shorter, which results in shorter days, right? So this is for the sun, but the planets also have seasons like this, right? So for example, Jupiter will sort of be at its like summer solstice point in 2025, and it was all the way in like winter solstice at 2019. I'm only saying like summer and winter in like a metaphorical sense, right? It's not really truly like summer and winter here on Earth, but it's sort of a similar concept, right? So that means that at northern latitudes, there are certain stretches of the year where they can like see the planet more clearly. But let's say the planet starts moving southwards, like towards the southern parts of the ecliptic, then you might end up having the planet like sinking below the horizon, and you might not be able to see like Jupiter for like the next few years or so until it like starts like climbing back up the ecliptic. So that's quite sad, right? But luckily for us, like on the equator here, we don't have this problem, right? Exactly because the ecliptic cuts like the sky at quite a high angle. So we are never going to have the issue where the planets will just like set below the horizon and it can never rise up again. Right. So after all of this, you can sort of like bring everything and thread them together in what is called the Sun-Earth frame. So why do we want to consider like a stationary Sun-Earth frame? It's precisely because like some kinds of planetary phenomena happen because of the planet's relative position to the Earth and the Sun, right? So that means that if you just fix the Sun and you just fix the Earth as like stationary, and then that makes like explaining like certain planet motion much more easier, right? So the effect of this is that even when we fix the Earth and the Sun, the planets are moving, but at a different speed, and the stars are moving in the opposite direction, exactly once per, like 360 degrees per year, right? So this is a table that sort of like summarizes what happens when you switch towards a Sun-Earth frame, right? So in a Sun-Earth frame, our origin is still fixed at the Sun, and our Earth is fixed, our Sun is fixed, but the stars are moving opposite, in the opposite direction as like Earth's orbit around the Sun. So you know Earth orbits counterclockwise around the Sun at 360 degrees per year, but the opposite happens when you switch to a Sun-Earth frame, right? So you have the stars like moving clockwise, like at a rate of 360 degrees per year, right? And that means for the planets, you actually can do a simple subtraction, right? So you just take the speed of their motion around the Sun and just subtract away the motion of Earth's speed, right? So this is precisely what I was talking about just now, right? So when you switch towards a stationary Sun-Earth frame, your distant stars rotate. You rotate clockwise at 360 degrees per year. Because your inner planets are faster than the Earth, when you subtract away Earth's velocity, they still look like they are moving all counterclockwise. But for your outer planets, they seem to orbit clockwise precisely because your Earth is orbiting faster than them, right? So if you like equations, this is what you get. But honestly, an easier way to visualize this is with velocity arrows, right? So in a heliocentric frame, this describes like how fast the planets are moving. So if your planet is moving closer like is closer to the sun, it appears to be moving faster, and the speed sort of decreases as you move out, right? So this blue dot right here is Earth. And if you just flip this arrow and subtract it for everything, then you can see that your inner planets will still continue to rotate counterclockwise around the sun, but at a much slower rate. While your outer planets will start going around the sun in the clockwise direction, but at a slower rate than the background stars, right? So if you sort of like think about it, all of this still adds up. It still makes sense, right? Well, with respect to the stars, your outer planets are still going around counterclockwise around the sun. So this all adds up. No funny business going on here. But you're just like changing your perspective, so to speak. Anyone confused at this point? All right, right? Okay, I think that's a yes. Okay, that might seem confusing, but I think there's actually quite a natural way to tie in the idea of a Sun-Earth frame, right? So as I mentioned just now, there is a natural association between like directions in space and time, right? So imagine if you go outside to look at the sky every night at the exact same time, at let's say 12 a.m., and you're looking at this direction of the sky, right? So you realize that like you just do that every day, every single day. Even your Earth and the sun is moving, your position with respect to the Earth and with respect to the sun is still the same, right? You're still always on the opposite side of the sun, looking at the opposite. You're looking at the part of the sky that's opposite the sun, right? So in a sense, you are living inside a fixed Sun-Earth frame. And from this perspective, you can see the stars sort of like moving like from in the clockwise direction, right? So that means that over the course of a year, you can see like the stars rising at an earlier and earlier timing. So when you switch your Sun-Earth frame, there are sort of like some terms that we use to describe the position of a planet relative to Earth, right? So some important ones that I need you to take notice is opposition. So this happens when a planet is directly opposite the sun. Then you have inferior conjunction, which happens when an inner planet passes in between the sun and the Earth. Then you have what's known as the greatest eastern and greatest western elongation. This is something that applies really only for inner planets, right? So as you can see from this diagram, this is exactly the point where the inner planet is at its farthest away from the sun, right? So if your planet is all the way here, the angle between it and the sun is sort of narrower, right? And if it moves ahead in its orbit, then you can see this angle is also narrower. So this is where our greatest eastern elongation is. So with this, we can sort of define the idea of what's called a synodic period, right? So the synodic period is exactly the amount of time that it takes for a planet to basically orbit around back to the same position relative to the Earth and the sun. So some more concrete examples of what synodic period would be is, let's say, the time between each consecutive full moon. Because as you know, a full moon only happens when the moon is directly opposite the sun. So in other words, when the moon is at opposition. Right, another example would be the synodic period of Jupiter, which corresponds to like the time between oppositions, right? Which is sort of self-explanatory. And for example, and another example is the synodic period of Venus. So you can take it to be the time between consecutive inferior conjunctions, or you can take it to be the time between consecutive western elongation. Well, basically, all it matters is that this is equivalent to the orbit, to how fast your planet orbits back to the same position, at least in a stationary sun and Earth frame, right? So this is the formula for synodic period. Even though it's a formula, right, it's still quite like a simple concept to understand. So this right here, where we take the speed of the planet and we minus off the speed of the Earth, this just describes how fast the planet is like moving around in this stationary sun-Earth frame, right? So you just do a bit of like subtraction, you just get this. And basically you're just taking 2 pi, which is the, basically, it's just a conversion factor, but it doesn't matter. It's basically just taking the distance that the planet is traveling, like 1 round, divided by the speed. So this gives you the time that it takes for it to orbit around the sun once. But from this, we also can deduce like a more like convenient table of values, right? That sort of gives us a better idea of how fast the planets are moving relative to the Earth and the Sun as a fixed like points. So Mercury has a synodic period of like 116 days. Venus, it's far more longer at 1.6 years. For Mars, it's the longest at 2.1 years. Jupiter, Saturn, Uranus, and Neptune, as you can see, their synodic periods are very, very close to 1 year, right? So the overall effect is that if you change like the distance the planets are away from the Sun, if let's say you have a hypothetical planet that has a very, very, very tiny orbit around the Sun, its synodic period will start to approach like how long it takes for it to orbit around the Sun, right? So you can imagine you're looking at this planet out there, like let's say something that's like closer to the Sun than Mercury, like let's call it Vulcan, then you can see it buzzing around the Sun like this, then it does make sense that each time the planet makes one round on the Sun and rotates back towards where it is, the Earth hasn't really moved much with relative to this planet, right? So that means that its synodic period is mostly very, very close to its own orbit around the Sun. But let's say you're talking about a planet that's very, very far away, right? That's very close towards the distant stars, right? Then the distant planet has barely moved, while the Earth keeps like moving around the Sun. So every time it returns to the same position, the same relative position, this is something that's like close to 1 year instead of like being close to the period of the planet. So we can also do a bit of perspective switching, right? So the reason why everything makes sense that way is because from our perspective, Jupiter is a superior planet. So that's why its synodic period is close to 1 year. But for Jupiter, Earth is an inferior planet. So from their perspective, the synodic period of Earth is very close to 1 Earth year, right? So in fact, the synodic period of how do I put it? The synodic period of Earth, if you're living on Jupiter, is exactly the same as the synodic period of Jupiter when you're someone living on Earth. So it's actually equal from both sides. Because the synodic period is precisely just defined by the relative positions of, let's say, Jupiter, the Earth, and the Sun, right? So as long as it rotates and goes back to the same orbital configuration, then this is our synodic period. And this is independent of like from which perspective you're looking at the whole system from. Right, so the same thing can be applied to like for inferior planets, right? So Earth is a superior planet to Mercury and Venus, but to Mercury and Venus, Earth is a superior planet to Mercury and Venus, but from the perspective of Earth, they are inferior planet to us. You can see that how this orbital period thing sort of like start switching over, right? So from all of this, what's the point of learning all of this, right? At the end, we sort of want to answer the question, when is the best time to look at a planet? So in other words, we want to answer the question, when exactly can we see the planet? When is it in season, right? So for superior planets, the answer is quite short, right? So the best time to see a planet is during opposition. And the time between opposition is exactly equal to our synodic period, right? So you know that for Jupiter, Saturn, Uranus, and Neptune, this synodic period is very, very close to 1 year. So if you subtract off 365 days, there's sort of annual lag time of 34 days for Jupiter, 13 days for Saturn, 4 days for Uranus, and 2 days for Neptune. So what this tells us that if opposition happens, like for Jupiter, opposition is around October this year. That means next year you'll be around November. Then the subsequent year, you'll be in the next month in December, right? So for Jupiter, there's this sort of neat pattern where every year it crosses, it's sort of like delayed by 1 month, right? So you have to wait 13 months in order for Jupiter to keep coming back into opposition. So same thing for Saturn, opposition keeps happening at a sort of a later date every year at 13 days each time, right? But as you go out to the further planets, you can see that this number of this time lag sort of like strings and strings and strings to like basically being nothing, right? And this is exactly because this time lag represents like how far the superior planet has sort of like moved along in its orbit, right, within the course of a year. So you need to spend this extra time for the Earth to basically go around the Sun and finally catch up with the planet. So for Mars, I put the timeline here as being 50 days. But as you know, because the synodic period of Mars is 2.1 years, that means that you only really get to see Mars like once every 2 years, right? So every 2 years, Mars will appear, but at a time period of the year that's like 50 days later, offset. So 50 days is about 2 months. So let's say in 2022 January, like, okay, 2022 December, you can sort of, okay, that's too difficult. So let's say in 2020 January, you sort of see like Mars appearing, then that means that you wait 2 years, right? And plus 50 days, which is around 2 months. So there will be around 2022 March, right? So this sort of tells you, like, gives you a very rough sense to like how to estimate when would a planet appear again, based on like when can you see it right now. By the way, the dates I gave are like sort of like inaccurate, so don't take my word for it. Wait, did I cover this already? Yeah. Okay, so the time between opposition is exactly the point where the planet is directly opposite the sun, as I mentioned before. But conveniently, there's also some things about opposition that we can sort of deduce from this diagram, right? So this, like, all these conclusions, they are something that you can sort of like tell directly just by looking at the diagram, right? So first thing, you know, at opposition, the sun is directly opposite the sun. Second thing, you know that the planet rises at 6 a.m. and sets at 6 p.m. precisely because you can start using a right-hand rule and apply rotation, right? So you know that at this point, the sun is setting. Wait, sorry. I messed up. Okay, the planet rises at 6 p.m. and sets at 6 a.m. So that means that because it's directly opposite the sun, then it makes sense that at sunset, you will see the planet rising in the east, right? And then at sunrise, you see the planet setting in the west. The third statement is that the planet is at its highest point in the sky at local midnight. Does that make sense to everyone? Right. So the fourth point, the planet is at its closest point to Earth. Okay, that makes sense. Fifth, the planet is basically at its largest and at its brightest, right? So this is a consequence of like the distance between the superior planet and Earth, right? So because it's so close to Earth, that means it appears to be far larger than if it were like at this point in its orbit, or if it's at this point on this orbit. And because it's also larger, this also means that it appears brighter to us. So this is why like opposition is considered the best time for us to be looking at a planet. So the last thing is that the planet will be in retrograde motion towards opposition. This is something that I'm deciding to leave to cover in the second half of this talk for now. So this is an overview of the planetary oppositions that are going to happen for this year, right? So the ones that happen already are Jupiter and Saturn at September and August respectively, and as well as Neptune. But Uranus and Mars will be coming up, right? So you can see like this here, over here is all the list of where their home constellations will be, right? And the dates of opposition are precisely when these parts of constellation will be directly overhead at local midnight, right? So this also sort of like corresponds to in which season like these constellations will be, right? So Mars is at opposition at December, which is during winter, and it's also in Taurus, which is a winter constellation. So same thing, Jupiter is at opposition during September, which is during autumn, and Pisces is like sort of an autumn constellation. So you can sort of like relate the position of planets to the opposition and the seasons in sort of like this like nice way lah. So as you might notice, for this year, all of the dates of opposition, they're quite close, right? They're quite clustered together in this like part of the year. And there is a very direct relation between like when opposition happens and their actual position in the night, in space, right? So if you look at this diagram, this is basically telling us where all the planets are exactly physically in space at this point in time, right? And you can see that Jupiter is here, Mars is here, Saturn is here, Neptune is here, Uranus is here. They all just all happen to be on one side of the solar system in like about like 1/3 lah, of like the entire like 360 degrees, right? And this makes sense because if you look at the table, like all of these dates, they're all quite clustered together in basically 1/3, in like 1/3 part of the year. So you can see that these dates, they correspond directly to where the planets are in the point in their orbits, right? this is related to what I said earlier about certain parts of the sky corresponding to certain parts of the year. So you know that Mars will sort of like be at opposition at around December. So that means that in this direction, roughly speaking, this is where the December winter sky would be. And over here, it would be where like the autumn sky would be. And this, yeah, right. So amongst all the superior planets in the table, Mars is sort of an oddball compared to them, right? Because as you can see, for Jupiter, Saturn, Uranus, and Neptune, their synodic periods are very, very close towards a year. While for Mars, it's at a longer like time period. And this is related to like their orbital distance from the sun, right? So as I mentioned like all the way in the earlier point, all the inner planets toward up to Mars are sort of like clustered together in very, very tight, small orbits. While all the outer planets, they are all like flung out in like larger orbits, right? And it's due to like this difference that you have this sort of like big difference in their synodic periods. So you can sort of like attach a more intuitive understanding of what synodic and sidereal period means, right? So roughly speaking, we can think of like the synodic period as how much earlier the planet would rise each day if we go outside and like look at the sky at the exact same time. While the sidereal period, obviously, it refers to how fast the planet appears to move with the background stars. But at the same time, we know that the stars appear to rise earlier each day, right? So the net effect is that for Jupiter up to Neptune, it's the annual motion of the Earth that sort of dominates, right? And Jupiter and Neptune, they basically don't move like during each time you get close to it and each time it's close to opposition. So basically, it basically looks like it's moving together with the sky. And like more or less at the same fixed point, right? So if the sky rises earlier each day by around 4 minutes, Jupiter, Saturn, Uranus, Neptune, they are basically going to rise earlier at around like 4 minutes each day as well. So not much there to see, that's pretty easy to understand. But for Mars, because it has such a long synodic period, the effect is that Mars seems to like appear to linger in the sky while Earth is like slowly trying to catch up. So what do I mean by this? Like here's a more concrete visualization of this like lag effect, right? So I'm not sure if you can sort of see this thing right here is Mars. And everything, all the stars here are in the background. And if you pay attention to it, the sky seems to be like going and moving ahead while Mars is sort of like falling behind. And if you do a bit of calculations, you know that from this, Mars rises on an average of like 1.9 minutes per day earlier, while the sky sort of rises at 4 minutes per day earlier, right? So that means that so that means that for most part of its orbit, Mars seems to keep lagging behind where the sky is moving, right? So it's because of this time lag that allows us to sort of like see like Mars stay in the sky for a longer and longer period of time. And this also relates back to how like the synodic period of Mars is longer, right? So yeah. Anyone wants to continue looking, or can you understand this? Yeah. So by the way, I only say that this is on average, right, for Mars to rise 1.9 minutes earlier per day, because this number sort of changes depending on like what's the relative position of Earth and Mars, right? So this is exactly what happens for retrograde motion, right? So as Earth like approaches Mars, the angle, like how fast this angle with the sun changes is also like changing at the same time. So that means that on some days, like it'll be slower than 1.9 minutes, and on some days it'll be faster. So this is really an average, right? But this is sort of like a useful tool for us to really like understand like how long do the planets sort of like linger in the sky, like on average, right? So what are the two factors that affect it? The first thing is its synodic period, which is like how fast the planet is moving relative to the Earth, right? So if you can imagine that if the Earth is orbiting around the sun and the planet is very close to it, that means that its orbital velocities are going to be very, very similar, right? So that also is why their synodic period is long. So that means that during each opposition pass, their relative velocities are very close together. So you can see like Mars is sort of like sticking and following like the Earth very, very closely behind. So judging by that effect alone, we should expect that longer synodic period will mean that the planet sort of like stays in the sky for much longer. But there is a second effect, which is like this is dependent on the geometry of orbits, right? So because, I don't, wait, do I have a diagram? Okay, so if you just draw concentric circles, right? If your two planets are very, very close together, that means that the angle, the part of the orbit that you can sort of like see is sort of like restricted. So I think I have a better diagram in the next slide. Right. So we can just do sort of a naive calculation. So for, let's say you have two planets whose orbital radii are very, very close together. You can see that this angle is sort of like quite small, right? As compared to, let's say, if you have this planet that's like all the way right here, then that means that the point at which the planet is at right angle towards the Earth is much, much bigger. And why does this matter, right? Because if a planet is exactly at this point or at this point, that means at midnight, you won't be able to see it anymore if it's like past this point. Because this is where like sort of like where your horizon line is, right? If you're looking up at the sky during midnight. And that means that if the planet is right here, you probably won't be able to see it during midnight. So we can just use this as sort of like a rough gauge for when a planet will be at its most visible, right? So the effect is that if you increase this distance between increase the distance of this planet all the way here, this angle will be bigger. But let's say if you increase this, like move it all the way closer towards Earth, the angle here will be much more smaller. Does this make sense to people? Right. So that tells us that we can sort of estimate like how long a planet will be up in the sky as the time it takes for the planet to sort of like travel from this side of the orbit all the way towards this side of the orbit. So that means that we need to find this angle and sort of divide it by like how fast the planet is moving in this stationary Sun-Earth frame. Can follow? Right? So this is just the basic concept, and if you understand it, that's enough, right? If you want to do the math, that's something you can do on your own free time. I can tell you that this is the expression you'll end up getting, right? But then the interesting thing is this is sort of the approximate visible time window for each planet. So for Mars, you can see the amount of time will sort of like be visible, like hanging around in the sky, will be let's say around like 200 plus days. Or for Jupiter, Saturn, Uranus, Neptune, it's very close to half a year, right? In fact, the farther out you go, the closer this number will approach towards half a year. And this sort of makes sense, right? So if you think about it, like the very, very distant stars, they don't appear to move at all. So that means that over the course of a year, you only be able to see them like half of the time as you like move around the sun. So it does make sense that this visibility would seem to get closer and closer towards half a year if like you're talking about a planet that's like very, very far away and moves very, very slowly with respect to the sun. If you plot out a graph, this is what you get, right? So graphs aside, there's actually an easy way to understand like why there is a difference between like, you know, Mars and Jupiter, Saturn, Uranus, right? So Mars appears to break the trend because like 208 days is more than half a year. While all the other planets, they are less than half a year, but the farther out they get, the closer their orbits get, the closer this time gets towards like 1 year. So if you plot out the equations for it, this is what you get, right? So this tells us that Mars is somewhere around here, while Jupiter is over here, Saturn, Uranus, Neptune, like farther out, right? So in this part of the graph, this tells you that it's the relative speed between the two planets that dominate, right? So because they're close together, they are moving very, very slowly relative to each other. And this causes them to sort of like appear and hang around in each other's skies for like very, very long time, right? And in fact, if you see this number approach towards 1, so that means that the closer it is towards exactly Earth's orbit, this number sort of explodes towards the infinity, right? So it makes sense. If your planet is exactly where the Earth is and keeps following it around, it will forever stay in the position in the sky. It will never ever leave your view, right? But when it's all the way far out, then you can sort of see that you can only see it half the time when you're in a part of the orbit where it's like facing that part of the sky. While the other half of the year, your planet will be sort of like near where the sun is. So that means that you won't really be able to see it during the night time at all. Are you following so far? Right, so this is just part one of the talk. What I'm planning to cover for the next part of the talk is really about the difference between inferior and superior planets, the concepts of the relative angles between the sun and the planet, right? Because unfortunately, planetary motion can be a lot more complicated than this. So this is really just setting sort of the ground-based knowledge that you need to go on and further understand how planets move in the sky, right? So that's the end. I hope I didn't scare too many of you off from coming from the next part of the talk. But if anyone has any questions at this point, feel free to raise it, and then I can go back and clarify whatever that needs to be said. Anyone got questions? Everyone can understand? Okay or not? You give me more confidence, man. Your of course doesn't sound very convincing. Nice. Okay, okay. Mm-hmm. This one?
The photo which you're showing right now again, what he's asking is taken from Selenium software.
This one's not. No. This one's the actual photo that people took. Yeah. Stellarium won't be so nice one. If no one has questions, then you can go on with